Las charlas técnicas de la Conferencia Internacional de Soldadura y Unión de Materiales. Quisiera hacer unos anuncios previos a las charlas propiamente. En primer lugar, al igual que el día de ayer, contamos con traducción simultánea para las personas que requieran el dispositivo para la traducción. Pueden acercarse a la puerta del lado izquierdo. Allí van a encontrar una estación donde pueden recoger los dispositivos para la traducción simultánea. El programa para el día de hoy contempla las charlas magistrales, así como también ponencias tanto en este auditorio como en el auditorio de Ciencias Sociales. Luego de esta ponencia haremos un pequeño receso de 5 minutos para que las personas que quieran asistir a las ponencias en el auditorio sociales puedan caminar hacia allá. El día de hoy, además, a la 1 de la tarde vamos a tener el segundo encuentro panamericano de soldadura, el cual se va a realizar en las instalaciones donde se están llevando a cabo las charlas técnicas. Van a haber personas que pueden llevar a los interesados al auditorio donde se va a desarrollar este encuentro. Este va a estar a cargo de Jorge Huete de CESOL y de Cecil Mayer del Instituto Internacional de Soldadura. Esto va a ser a la 1 de la tarde. Yo volveré a hacer este anuncio también en el intermedio, por supuesto, antes de que acaben las ponencias de la mañana. Bien, dicho esto, entonces vamos a empezar el día de hoy. Para mí es un placer presentar al ponente magistral de esta mañana. Él está con nosotros desde la primera conferencia, es decir, esta es su cuarta conferencia internacional de soldadura. Es realmente un referente para nosotros en el campo de la soldadura, asimismo como en el campo de la academia y de la investigación. Él es el doctor Stephen Liu. Él recibió su bachillerato y su maestría en Ingeniería Metalúrgica por la Universidad de Minas Gerais y su doctorado en Ingeniería Metalúrgica también por la Colorado School of Mines. Él es fellow de la Sociedad Americana de Soldadura, de la Sociedad Americana de Materiales y de la Sociedad Americana de Ingenieros Mecánicos. Ha recibido además múltiples premios y distinciones en el campo de la soldadura y la ingeniería de materiales. Sus intereses de investigación están enfocados en técnicas de unión, ha publicado extensivamente todos sus trabajos de investigación y actualmente es el director del Centro de Investigación en Soldadura, Técnicas de Unión y Recubrimientos de la Colorado School of Mines. Dr. Liu, it's a real pleasure for us to have you here. This is your 4th conference. It's an honor for us to have you in all this conference, and we really appreciate the time that you take to come here with us to share your expertise, your knowledge. We are very happy to count with your collaboration, but especially because, as we have talked before, we consider you as a very good friend of the university. Thank you for your contribution with our field.
Thank you.
Les recuerdo, por favor, apagar sus celulares o ponerlos en modo vibratorio en todo caso. La dinámica de las charlas es, bueno, tenemos ahorita la presentación magistral y después tendremos 2 ponencias en las cuales sí habrá al final una ronda de preguntas. Dr. Liu.
Okay. I'm unsure if the speaker is working. Is it working? Yes, okay. Thank you. So the title of the presentation is Research Primer on Understanding Laser-Based and Electron-Based Additive Manufacturing. It's a little bit off from the traditional welding and joining sense. So this is me, and I hold the American Bureau of Shipping chair. And this event here, of course, is the ICONWELD. So this is the 4th conference, and also the 2nd encounter, the Pan-American encounter, and it's happening here at the Catholic University. No? Okay. Now it's working. The sound. No? Not working? Oh. Oh, okay. It's not working for you. Okay. All right. Can you hear me? Partially. Now, if I walk a little bit and say, can you hear me? It's better this way? Oh, now it's okay. All right, all right. So can we resume? Okay. All right. So, okay, let's go to the next slide here. And first of all, I want to congratulate the Catholic University for the 100th birthday. And actually, this is the 101st year, because you were established in 1917, but so that's the 101st year. And the most important thing, though, is that the graduate school was established in 1984. So that's quite a few years ago. And the Catholic University is recognized as the best university in Peru, and with world ranking. So congratulations. So here we have this, what a milestone. Okay. All right. So I want to just very briefly talk about my past association with the organization of the International Conference of Welding Joining of Materials. So you see here on the right-hand side here, the first one was in Lima, the second one was in Cusco, the third one was in Lima as well. So those are the 2003, 2007, and 2010. For the first two, actually there was a symposium to go with each one of those, so I was fortunate enough to be part of that program. And I want to show you a few pictures of who are the really relevant people that organized this meeting. And you see here, there's Dr. Jorge Merztal, who was there. And in the picture, who else is there? Ernesto Indacochea. And it's international, Dr. Tom North here from University of Toronto. So, okay, so from the 2010, this one was most festive. You see Professor Carlos Fosca here and Jorge Merztal here. And it was truly international because the Osaka professor Ikeuchi and Wolfgang Tillman, and then Ernesto here again, and I think that's Carlos from Sodexa. So let's look at the next one here. American Welding Society actually looks upon this event quite seriously, because you look at here, one of the former presidents, the Big John. So John Bruscotter, he was here, and here Professor Carlos Fosca is here again, and Jorge Merztal and Ernesto. And then so finally, that was in one of the welding shows, and here Professor Rumichi here, right there. I won't call you younger than. And so here. One person that I want to mention is Professor David Olson. Professor David Olson, despite showing up only in one photograph, he was in all the other conferences as well. And John Dupont from Lehigh University, he also participated in the 2010 Lima. And then the first Pan-American Welding Congress, I was fortunate enough to participate, and that happened in Brazil in 2014, and this is the second of the Pan-American Conference. So Dr. Cecil Maya was here, so and Daniel Jalmeida was here. So okay, now we can go back to the actual talk about for the day. Okay, so we're going to talk about additive manufacturing, laser-based and electron beam-based. I know that on the program there will be one keynote that will be talking about arc-based 3D printing as well, so we're not going to talk about that. So if you look at these gadgets that is shown on the slide, you notice something. These are all gadgets, as they say. On the left-hand side here, you have an octopus, and with 8 tentacles. Each one of the tentacles have 9 joints. They are all linked joints, and they are all built at one time. There was never an assembly that put the different sections together. In the middle here, there you have a chest piece, okay, the rook. But look at the details that you can build. Here you have a little stairwell that goes down the chest piece. And this, again, is built layer by layer into one single piece. On the right-hand side, you have Lady Liberty, that so proudly stand in the New York Harbor. And you have the torch, and then look at the details that you can build out of 3D printing. And there's a tablet that she carries. So sometimes I wonder that if you wonder what is written on that tablet, okay, I'll tell you, it's July 4, 1776. That's the day of independence of the United States. And then another probably a trivia fact as well is that right by her feet there was a broken chain as well. So meaning that she broke free and now it's liberty, it's freedom. So these are all things that we can build using 3D printer in a single operation, okay? Now, what is the problem then? So let's look at this. If you look at here, you look at the surface, look at here. The surface condition isn't so great, okay? So each piece here, you can see that there are, look at that, the surface roughness. So one of the shortcomings of 3D printing is going to be the surface. How can you produce a better surface from these 3D printed materials? Okay, now, you look at this one here, making it more like an engineering piece of material. You have here a model engine, okay? Now, I don't think this is an actual working engine, but yet it was printed one piece with a free rotating rotor. Okay, that is already an accomplishment. So let's get closer to the actual printing. GE had announced that they actually printed this piece of machinery. It's an ATP engine, okay? And this supposedly was the first engine that was printed all by 3D printing. Now, sometimes I'm not exactly sure at what stage we are, but they claim that they have built one. So let's take their word for it. But I'm going to go back to some more of the engineering components. So here is a jet fuel nozzle, and this is actually built by 3D printing, okay? If you were going to do this by manufacturing, the more conventional manufacturing, this part here could be anywhere between 20 to 50 parts and then brazed together. So just by doing the 3D printing, and this is done by laser powder bed fusion, that is a tremendous saving, okay? And this is a real part that is printed that is in use, actually. All right, so now this one here, you won't believe it, how close to commodity manufacturing it is. This, if you look at the bottom here, it has down here, it says Costco wholesale. So Costco, Sam's Club, you know, these are wholesale retail stores. You go in there, what do I see? I see a 3D printing system, okay? So this machine here, let me just change here. So this machine here is a 3D printing machine sitting in the middle of Costco. So I very quickly, I said, what is this about? So I look at this chamber here, which is this one here. It has print and laser drawer number 1, print and laser drawer number 2, print and laser drawer number 3, okay? And so I'm going to go to the next slide and do look at here, this part here and this part here, because it is actually working here. Can I get that? Oh, it won't play? Okay, well, it won't play. But it's actually printing on site. What does it print? Insoles. Insoles for shoes, for tennis shoes, running shoes. And the cost is about $130 per pair. Kind of steep, very expensive, okay? But it is there. So, ladies and gentlemen, 3D printing is here, okay? All right. And this is a powder bed fusion machine. So this machine is yay big, EOS, if you're familiar with the 3D printing processes. So here you look at it, there is a little bit of a scanning, the laser is scanning there. You can see, I took the picture too early on the process, and you see some little sparks and all that. That is the interaction between the laser and the powder and so on. So by repeatedly scanning this powder, you locally melt that powder into one single part, and that builds layer by layer, however long it is. and the length or the height of that depends on your chamber capability. Most of the time today, that is the limitation, about 12, 14, 16 inches tall. So a part can have that volume, okay? All right, so what have we done that I wanted to talk to you about 3D printing? We have been looking at electron beam freeform fabrication. So that is the electron beam process to build 3D parts. Laser powder bed fusion, so the PBF process, and also the laser direct energy deposition. So we have actually worked in this field in all those three. CSM also, Colorado School of Mines, also has another entity. It's called the ADAPT Center. ADAPT Center and the Welding Center, they are parallel. ADAPT works only with 3D manufacturing, but they are far more into the process modeling, mathematical models for the process and output characteristics, and also product characterization, while we do most of the material characterization. So here's a little bit of the history of what we have done. We have started about in 2008. And so here are some of the students, and the blue ones are the current ones. So if you go through that, we have 6 graduate students working on it and 1 visiting professor collaborating in this effort. And so the first part that I'm going to talk about is the electron beam freeform fabrication. So we have experience in aluminum alloys, titanium alloys, and the composite material, aluminum silicon carbide alloys. And the last group is in situ composite. So you'll see in a minute why we put so much emphasis in the in situ composite. So this is one of the questions that a friend asked me, said, why do you want to do 3D? If you have a part that has been rolled or forged and heat treated, you will never be able to build a part out of 3D that is comparable. I said, well, you can have this part built 3D and then HIP it, hot isostatic pressing, for example, and then heat treat it, you will develop the property. So this slide here tells us a little bit about that. So the slides here shows you the blue one is the S printed. They are pretty lousy compared to the one that is deposited plus a T62 processing, which is heat treated. If you look at the ultimate tensile property, it is still pretty lousy. But when you compare the green one here and the gray one here, look at the gray one, that's the T62 typicals. That would be the typical T62 on a 2219. They are very comparable. If you look at here, they are very comparable, and they are very comparable. So it is possible to do 3D printing followed by several post-processing methodologies. But one of the major things that happens in 3D printing is that you have a composition modification, composition change. Once you print it, you seem to lose alloying elements. So the aluminums, the manganese, the vanadium, they seem to lose from, for example, a Ti-6-4, titanium 6 aluminum vanadium alloy. And you see that this would be the 6% nominal. If you were building Ti-6-4, you have a loss of approximately 1%. And so that is more comparable if you had started out with a Ti-7-4, okay? So there is something that you need to learn how to work with it. So what we have done was to use a powder core wire. So you put in your correction of the chemical composition into this powder core. And then with that, you see here, your alloy composition falls back to the original 6% of the Ti-6-4. So it is possible to do that. And so here I will compare for you 2 different processes. One using what we call the monolithic Ti-6-4. The other one is the powder core Ti-6-4, so that you see the differences between them. Look at this first one here. This is made by a monolithic wire, which means a solid wire deposition using electron beam. So the electron beam hits the wire and then deposit onto your substrate. And so here on this diagram here, you have 12 layers building on top of each other. On the right-hand side here, it's not that important, is that it will show you some of the metallurgical phenomenon, such as banding and the microstructure. But the important thing is that you see the tremendous amount of epitaxial growth. So the grains will continue from layer to layer, from layer to layer, okay? But no defect, no visible defects. If we switch that to the powder coat to compensate for the composition loss, what do you see here? You see the presence of pores. So because of the inherent properties of the powder that you use, when you deposit, now you generate these porosity. Now, what are these properties? What are these characteristics? Maybe oxygen, maybe nitrogen. So some of these oxidation products, they decompose and then release it. So now you have all these. But the characteristic of epitaxial growth continue, okay? All right. It can be removed, okay? So here you see a lot of pores, and here you don't see any pore. The change is only current. So using process parameter can correct for these properties, okay? And in fact, here's a graph that shows you decreasing amount of porosity with the current level. So it is possible to mitigate all these. Now, another set of possibility to mitigate is by modulating the current. So instead of using a continuous current, what if I use my electron beam by pulsing the currents? Okay, so you can see that, I'll skip to the next one. This one here only shows you the presence of the chemical composition segregation, okay? So the next one here, you see the left-hand side, okay, the continuous epitaxial growth. On the right-hand side here, you still see some epitaxial growth, but those grains are beginning to get broken. And that is all by modulating the current, okay? And the finer microstructure also shows that there is a refinement of the grains. So that is great. So here on the left-hand side, you have the pulsing of the currents. And then on the right-hand side, you see here, going from non-modulated to modulated, you have a refinement of microstructure. Again, I'm showing you that it is possible to change the macrostructure as well as the microstructure. Now, I, as a metallurgist, I like to see some phase transformations and some ways to affect the microstructure. In this case here, by adding some inoculants. So inoculation agent, look at the bottom right diagram here. You see this little dark particles here. That was because of the addition of a little bit of iron, and iron grabs the boron, forming FeB, and FeB will break up the aluminum-based microstructure, titanium-based microstructure as well. So it is possible then to combine between metallurgical as well as just process control, okay? All right, so this is the more hot topic these days, is that we want to use composite material for a number of reasons here, and these are the good things. You can see the UTS increase by going to a composite material. You can see the shear strength increase by going to a composite metal. So on the right-hand side here, you see a composite build. What happens there? The particulates do not disperse. That's the problem. They form clusters. And when you have cluster, you have just cut down on the effectiveness of the composite material. So then our job was saying, how do we do that? Okay? So there's some problems, some defects that goes with it as well, is that if you put in silicon carbide into aluminum alloy, the silicon carbide going through that arc source or going through the electron beam source or laser source, they will decompose, and the carbon will be picked up by aluminum as aluminum 4, carbon 3. And those are bad for the mechanical properties, crack opening, and so on. In this case here, you see on the left-hand side here, silicon carbide dispersed in aluminum. On the other hand is that the aluminum side, you also run the possibility of hot cracking as well. So then we thought, okay, what we can do is coat each one of those fibers. So silicon carbide, you coat it. So here, if you look at it, we tried titanium coating, magnesium coating, nickel coating, copper coating. We learned a lot, is that too thick a coating does not work. You know why? Because too thick a coating, that particulate will behave like a piece of metal. It won't behave like a ceramic particle. So thin coating is what works, okay? And so here, thin nickel coating and thin copper coated particles works better. It changes the distribution of the particle, allowing a little bit better dispersion. So there's a lot of modeling work that needs to be done in that part. And then the last part here is in situ particle formation. Instead of adding those particles in there, why don't we let those silicon carbide particles form in situ in the system? So we're working with a company who has the expertise of exothermic actually reactions in the melt pool to form these particles, because formation in situ will avoid this wetting and distribution based on the flow of the material of the pool. All right, so let's move on to talk about the powder bed fusion. So up to this point, we were doing the electron beam freeform. So powder bed fusion, and we have two pieces of work, one mainly on the PH-17-4 as a martensitic stainless steel, and then the 304, precipitation hardened, I should say, and then the 304 stainless steel. So we had a few questions. What we wanted to know is that, can we weld these AM components? People think about, so okay, I'll build these parts. But by building these parts, though, is that you still have the need, you may have the need of attaching several of these components together into a larger assembly. That's our focus there, is to, does the AM part weld just like a rod material? And we found that it does not, okay? And then the rest of it is more metallurgical. What does the AM microstructure, how does it affect the welding behavior? What about the texture that everybody talk about? What about the residual stresses and so on? So if you look at it, there's a whole list of keywords that you should be focused on. The powder processing itself, the deposition parameters, microstructure, composition, microsegregation, anisotropy, residual stresses, active whatever, I can't see the last line there. But all those are just on your platter. So it is really a banquet for materials engineers, for metallurgical engineers, for manufacturing engineers. Really great area to be studying. Okay, so we look at the 17-4 first. And if you first focus on the right-hand side here, so the dashed lines meaning the layers of deposit, okay? So they were all built from the bottom up. The dark line is the weld. So we welded it here going this way, and then the other one we welded horizontally, which means parallel to the build layer. One is transverse to the build layer, one is parallel to the build layer. Okay, so that's number one. You wanted to see how they affect, how the deposition scheme affect and the welding scheme affect the property. The other one here is that look at the base target composition of 17-4 and the deposited composition. Right away you see those red boxes there showing you the different composition that you get. So by doing that, you see the nickel composition particularly is different, going from the original nominal composition of 3 to 5 to about 8.6%. And then I'll point out the nitrogen composition, very much higher than what it is in the expected composition, and oxygen, 0.048%, also very high, too high compared to its composition. So here I wanted to show you only one thing, is that the weldability behavior, or the difference here. So you look at the left-hand side photomicrograph here, that is the AM of the 17-4, and you see a lot of these deposits. So each one of those actually is a deposit, and there are many little swirls, okay? So take a look on the right-hand side here. We took this little swirl here and then did an analysis here. You look at it almost like a composite material, because on one side you have a austenite, on the other side you have the martensite. So this side is more closer to the 17.4, but this side here is more like a nickel 718. So what has happened there? So now you have literally a repeating patterns of this world with different composition. So then a little bit of the TEM work here and also the STEM work. And you notice the nickel composition goes up, and it says that 718. So now that begins to bring in another question here. Did the manufacturer screw up in the sense that they mixed powder? Was it a totally, fully clean system before they started building the 17.4? So those are the questions that we have. If it were only by the welding, by the deposition itself, and it partitioned itself, distributes itself as the 718, we have a major problem to deal with to get it back to a more uniform composition. If it were more of an operation failure, then it's just by basically cleaning the system and all that. But that remains to be a problem to be resolved in the industry. Okay, and as a consequence of this change in composition, you actually change the microstructure, the solidification and microstructure as well. So the expected composition from the substrate here, and this is calculated according to the WRC index, so it positions here. So it is a ferrite solidification mode. But when you have a deposit, so these two deposits here, they sit up here. It may be a little bit too light for you to see, but they sit here. One is closer to austenite solidification. The other one is an AF. So it austenite primary solidification and then ferrite solidification. So if you plot on this diagram here, they represent these diagrams here, okay? Now, if you increase the cooling rate, then it shifts also to the right-hand side. And cooling rate is important in 3D printing because each one of those deposits are so small relative to the substrate. So there's a lot of metallurgical engineering work there. Another thing that we want to point out to you is that the material that you're welding also exhibits a great deal of differences as well. For example, when you weld on a wrought piece of material, 304 stainless steel, and you weld on a 304 AM'd material, you notice just the metallography preparation will tell you that something has happened here that is different. The heat effector zone size is different. The heat effector zone microstructure is different. So is it possible that the thermal conductivity has changed, the heat capacity has changed, heat flow behavior has changed? All those questions remains, to be answered, and a lot of the thermal analysis work can be done here. So to further look at this here, just by enlarging the left-hand side diagrams here, you have the wrought material. You can hardly distinguish the heat effector zone behavior, the heat effector zone microstructure. But when you look at the AM material, look at how clearly the microstructure developed. So those are other things that we need to be careful in. Another one is that looking at the AM to wrought material build. So this is dissimilar metal, so to speak, okay? So look at this zone here. By the way, we put down this, highlighted this boundary here, but the coloration is as what is shown here. So one side is greater than the other side. So the heat flow is not a balanced heat flow. And if you look at the weld morphology, so basically what we did is we copied the bottom side here and just superimpose here. Can you see that there's a region here that is not covered? There's a region not covered. So actually the weld pool that forms, I call it a weld pool, but it's the deposit pool, is actually different in shape. So again, this is a reminder that there are fundamental differences between the wrought material and the AM material. So now you look at the AM texture, so using electron backscatter diffraction, and so epitaxy is there. But epitaxy in these cases, in 304, it doesn't go through like the multiple layers as in the titanium case. In this case here, most of them will be going through maybe a couple of layers. And you can see that there are the white lines here showing you the bottom of the deposit. And then you see that there are grains that are, see here, it goes through about 2 layers. That's about 2 layers, about the average that we have seen that goes through. Okay, so another one on this side here. So, and here, this part here, I really want to show you here. Look at this bottom here. Okay, so each one of those are delineated by a yellow line, and those are the bottom of the deposit. You notice that they have different shapes, okay? So one is particularly wider. This one here is very wide, and this one here is much narrower. This repeats here, and so on. Now, when we show this to many people, they say, oh, that's just a different field of view. If you maintain the similar processing parameter, why would the different field of view matter in terms of penetration? It would not. The width would, okay? So there's something else to go with it. And one of the colleagues, Professor Badashi's student, you know, so Suresh says, you dummy, you know, it is Marangoni flow. So we're also looking into that. Okay, so here you see the epitaxial growth phenomenon. Okay, so again, another difference yet. You look at the rod product, welding on the rod product, welding on the AM product. The diffusion line, how uniform is on the right-hand side here, and how rough is on the left-hand, on the right-hand side here. So AM does have this problem, okay? Problem in a sense that does exhibit this heterogeneity. So you can calculate the solidification rate now. If you calculate solidification rate, you'll find out that AM actually has a lower solidification rate than the rod material. Quite interestingly, why should that happen? That's again the question that we're pursuing. Okay, all right. So look at this. These are gas tungsten arc welding. Okay, over the selective laser melting, which is powder bed fusion in this case here. The morphology is different by changing the heat input as well. So the aspect ratio of 0.43 on the left and then the 0.35 on the right. And if you look at the longitudinal transverse cross section, look at the bottom of the bead. You know, it has a lot more of these fluctuation. You know, it's not quite like the laser spikes or the electron beam spikes, you know, in the welding, but it does show that difference. All right, so it seems to me that I'm giving you far more questions than answers, okay? But that's okay, that's how it is. So this part here, we're looking at the direct energy deposition. The powder bed fusion and direct energy deposition is different. One, you have a powder that is laid down and then you would scan your laser. On this case here, you would have your laser and then you will have the different sources of the powder feed into the laser beam and then depositing. So we wanted to understand, would there be differences between the powder bed fusion and the direct energy deposition? And the answer is that there were differences, in fact, in terms of solidification and then anisotropy and so on. So here, if you look at it on the left-hand side here, it is the direct energy deposition. So these powder are fed directly into the weld. And you just look at the microstructure here. This is totally different from the right-hand side, which was powder bed fusion. Okay? On the right-hand side, the powder bed fusion, you know, enlarging it, you see here, it's a mixture of the solidification modes. Okay? On the left-hand side here, you have almost cellular structure. That is your austenite solidification. So there is a difference, but why should there be a difference? Okay, that's the whole question that we're pursuing as well. Another one that people look at a lot about anisotropy is the mechanical properties. So here, this is the look at the type of the tensile specimens. Some are parallel to the, so where the arrow is, those are parallel to the build direction. And then on the other side here, these are transverse, so they go in the direction of the build. So I'm going to go to the next slide here. You see that they are different. They exhibit different properties. So the blue lines here are in the build direction, okay, the blue lines, and then the red lines are transverse, orthogonal to the build direction. And invariably, the red lines have higher strength but lesser ductility. The blue lines with lower strength but higher ductility. So what happens there is the following. The blue lines are built this way, the samples are cut this way, and then the red lines are cut this way. If you look at this, this gives you some impression that could this be considered as a composite material actually? Because on the left-hand side, where this is, you have the fibers, so to speak, fibers built this way, and you're trying to pull it in this direction. So no wonder the properties are different. Now, we need to do more about that. And then we notice that there are some localized deformation, preferred deformation. Is it related to the different microstructures? So here, in this case here, this is the tensile direction. And then you notice that going across the sample here, there are regions here that have localized deformation. So taking a look at the light micrographs here, the Z and XY represented different views of the different materials. And so you see here, there are some features here that could be identified as maybe twinning, the results of twinning products, okay, and which is not as visible in the DED. So on the left-hand side is powder bed fusion, on the right-hand side is direct energy deposition. All right, so then you look at the EBSD, so you look at the image quality mapping, and you look at the phase map here, you see two different phases, the austenite and the ferrite, even though the ferrite identified here is very likely that of a martensite, for example. And this is the powder bed fusion. If you look at the next one, it will be the DED, direct energy deposition. You see somewhat of a similar, with different amounts of the martensite and the austenite and so on. But the X-ray diffraction shows you the best examples. So look at here, there are three different spots that we did the X-ray. One is from the grip, one is from the uniform elongation side, and one is from the post-uniform. So that is the non-uniform elongation. So let's focus only on the blue ones, okay? So here, if you look at the blue one here, if you look at the blue one here, across here, the DED, direct energy deposition, or the powder bed fusion, they all show the presence of martensite. So actually martensite form together with the, in the presence of austenite. So that makes the explanation of the properties. All right, so what is it that we look at in the future? So from this point on, what are we looking at? And this represents only our own views and what we are focusing. Custom design new material system of deep deposition, the core and the sheath material, metals and composites, and in situ composite development. We see that as an opportunity of really creating some different set of properties. Customized powder design and processing. I really think that we need some even better quality companies to, not companies, even better properties, processes, and for the powder properties, you know, really clean powder with little oxygen, little nitrogen, you know, to the composition that you do. Today, your powder may not be guaranteed, so atomization and all that still is less than desirable. Investigate effects of process variables on resulting chemical composition, microstructure, mechanical properties, understand the property and defect formation in the deposits. And for AM weldability, understand weld zone and heat effector zone formation for AM materials as a function of physical properties. Relate microsegregation to AM weldability. Characterize residual stress development in welded AM material. I think it is there because during the manufacturing, as you deposit the powders, if you don't manage it correctly, the deposited layers simply peels off to that extent. So that's kind of serious in that matter. More, the model, the cracking mechanisms in AM materials, particularly in the aluminum alloy systems, the more of the aerospace applications, they can become critical. Characterized mechanism in the AM weld, so additive manufacture, 3D printed. And then the next one is 3D printed to the wrought material, because you have to many times attach it to a wrought part. Develop the similar AM and AM wrought welds, so different material system. And then there is going to be a talk on the arc-based AM. So develop more of the arc-based AM capability and application. Customized filler for arc welding AM material. We, at the school, we have typically, we have an expertise, a niche in the consumable manufacturing. So we think we can apply our knowledge in that. Clarify the fundamental property, decipher how primary solidification differences occur in similar composition. I was referring to the powder bed fusion versus the direct energy deposition. Look at the differences in anisotropy, the mechanical property and fracture behavior. And then the last one, I think that's the final one, is the surface quality. We talk about all those, but we did not talk about surface quality much, is that the surface quality can many times be the, I won't call it Achilles heel, but it is going to be one of the weaknesses there. So what is it that we have acquired at our place? We are going to be getting a system, the arc-based additive/subtractive manufacturing. What this is that you build one layer, you machine one layer, you build one layer, you machine one layer. There's several advantages to do that. First of all, extremely good surface finish. Second is that you take out part, manage the residual stress as well. So that is going to be a joint effort, the CSM Adapt and the CWJCR, with a company called DMS and another company called BMA. And the equipment is going to be placed in my laboratory. And then we're also going to place a KUKA robot, which would be a central piece for the AM cell to be placed in our center. So with that, I'd like to acknowledge a few people. Professor Rumichi here of the university that organized the ICONWELD, Professor Carlos Fosca, and Dr. Jorge Merzdal, and Professor Ernesto Cochia. He was the guy that invited me, started me with this relationship with the ICWJM. So thank you. And my research team on AM, so Christine Hillier, Scott Mitzner, Devin Gonzalez, Cheryl Hawk, Ethan Davis, Jordan, and Ezekiel Pessoa. So with that, I thank you all, and I want to also invite you to work together with me, on this such an exciting field of engineering. Okay, thank you very much.
Dr. Liu, thank you very much for your very nice presentation. Thank you. Hacemos una pequeña pausa para que los interesados en las charlas del auditorio de sociales puedan dirigirse hacia allá y nos vemos aquí en unos 3 minutos para retomar las charlas de este auditorio.